Good morning. Let us continue our lectures devoted to application stochastic calculus to study functionals for linear processes. Namely, we want to study solution to stochastic differential equation, and in order to do this, we need more precise investigation of the extended of Skorokhod stochastic integral. Let me recall its definition. So, if we have a standard linear process, for example, in the interval 0, 1, then for any alpha which is square integrate and measured with respect w, there exists inverse function. Alpha can be expressed as a sum from n equal to 0 to infinity of such multiple linear integrals. Where we said that this is just a formal notation, and this integral must be defined as n factorial of the integral over simplex. Here, the n are symmetric functions which are square integrate over this cube. And after this, we define stochastic derivative of the random variable alpha. This is a sum it can be obtained from the previous series, just taken one variable as variable t, an t, t1, tn minus 1, dw, t1, dw, tn minus 1. Stochastic derivative of the random variable alpha is a random function. Of course, it exists not for every random variable, but when it exists, it satisfies good properties which we already studied in real analysis for usual derivatives, satisfy chain rule and other good properties. And this operator appears to be closed, densely defined operator in L2 sigma of W. So one can define conjugated operator. We denote it by I capital, conjugated operator, D star, and it is acting from L2 omega P L201. So it is defined on some functions, random functions which are square integrate into sigma W, and it also has a dense domain of definition. It is also unbounded operator, and last time we see some surprising properties of this operator. Namely, we already know that it is from one side some generalization of the partial differential operator of the first order, the divergence. And from other side, it is a real extension of the etostochastic integration. Namely, we discovered that if we have a square integrated random function, which is adapted to the flow of the linear process. So for x square integrate and adapted to the flow of W, extended stochastic integral of x coincide with the etostochastic integral xt t. So this is Skorokhod integral. This is Hitler integral. But of course, we have another examples of the random functions from the domain of definition of extended stochastic integral. And we finished last lecture on the formulation of the result, which shows this. Namely, it occurs that if the random function has stochastic derivative, if there exists stochastic derivative of the random function, then this function belongs to the domain of definition extended stochastic integral, and we have the following property. The expectation E of x squared is equal to expectation of x squared norm of x squared plus trace of dx squared. Here, norm is taken in the space L201. So norm of x squared is simply the integral from 0 to 1 xt squared t. And we discussed that dx is a random Hilbert-Schmidt operator in the space L201. So its square is a nuclear operator, and this trace then is well defined. So such a sum is appears to be equal to the expectation of the square of this extended stochastic integral. And before to prove this theorem, we made a remark that because of dx is not symmetric operator, it's not symmetric, that is only Hilbert-Schmidt operator. We discussed it in detail. Then this dx square can have negative trace, and then you see it can happen that at least now we can guess that it can happen that this integral can be equal to 0. So now let's try to prove this statement. Here I will use a way of the proof which we already used. Namely, I will try to consider a random function of the special kind. You remember that any random variable which is square integrate and measure with respect to w, any random function which is square integrate and measure with respect to w have e-to-winner expansion as a sum, infinite sum of multiple linear integrals. So, firstly, I will start with the separate summand of this series. So now I'm supposing that our random function is of the following kind. Xt is equal to integral from 0 to 1 n times an, it must depend on t, and t1, tn, dw, dw, t1, dw, tn. And you remember that now the expectation of the integral 0 to 1 xt square dt is equal to n factorial integral here from 0 to 1 have n plus 1 time, and here an t t1 dt excuse me t1 tn square d t1 dtn and dt additional value here, and here we have n plus 1 integrals, but n factorial. So when we have such a special random function, of course, it is clear that it has stochastic derivative, and we can write it. Let me do it using just a raising function. So now x has stochastic derivative, and dx d of s is equal to n. Here we will have n minus 1 stochastic integrals. Here we will have s, and then t1, tn minus 1. Here also dw, tn minus 1. So you see that obtaining derivative is a random curve. It depends on the two variables. One is related to the initial argument of our random function. Another one is the argument of stochastic derivative. So we have such a random Hilbert-Schmidt operator, or a random square integrated kernel. And one can even try to find the trace of this operator. So when we will have d xt s, and I want to multiply the square of this operator. So I have to apply it to dxs(r), and then integrate it with respect to variable s. ds. Yeah. Okay. This is the such operator which is related to such new new kernel. It depends on t and r, and this is dx. Maybe I will write here square from t and r. Yeah. Now we have the integral cap. Of course, it is not right way, rigorous right way of thinking. But let me just recall that in case when dx square is continuous kernel, the trace of this operator is just integral over diagonal. So let me keep this formula for general case. So just for a moment, write the formal relationship, which will allow us to get the flavor of what is the trace. What is the trace now? So now one can see, at least as I said, if this continuous kernel, that is rigorous, the trace of dx square is just equal. I must put one variable instead of these two, and then I will get another one side of integration. So we will have two sides of integration, and here we have dx. Let me say keep here t s d. Excuse me. D. Here we have x s t, and then ds dt. So we just have such a permutation of variables t s x t, and from this point of view, if we recall that this kernel is not symmetric, we have no reason why it is symmetric, then it's understandable that this quantity can be even negative. Now let's write its expectation. Yeah? It's also easy. It's also easy because it has this random kernel has a representation as a multiple integral, and from the kernel A. So in terms of kernel A, one can say that expectation of this trace of dx squared is equal to here we have we'll have a product of two multiple linear integrals of the same multiplicity n minus 1. So it is n minus 1 factorial, n minus 1 factorial. And here we have this dot integral from ts and st. So it will be like this. Here we'll have n minus 1, 0 to 1 integrals. Here we have 8n. You remember t, s, then t1, tn minus 1, multiply 8n. Here we have s, t, and then t1 Tn minus 1 ds dt dt1 dt1 dtn minus 1. Yes. And now I will do very formal thing, but it will be helpful. I want to have here all variables which are Tn up to Tn plus 1 enumerated as I said. Then let me just change notation for variables of integration. Variables of integration. Then I can continue with the following formula is equal to n minus 1 factorial. And here we have what? We have the integral from 0 to 1 n plus 1 time. Yes, we have n minus 1 to integral here. And then an t1, t2, t3, tn plus 1 multiply by an, and here t2, t1, t3, tn plus 1. Here we have this one, dt1, dtn plus 1. This all. So this is a final formula for the expectation of the trace of dx squared. Now let's find the same formulas for other members of the desired relation of the statement of our theorem. So let me write something. As you remember, the next member in the right part of our relation was just expectation of the integral from 0 to 1 x t square dt. Then is equal to n factorial, because xt is just n multiple linear integral, so put n factorial. Then here is integral from 0 to 1 because of this integral. Then multiple integral from 0 to 1 multiplicity n, because the kernel has this multiplicity. And an t t1 tn square d t1 dt1 dtn and dt. Again, I will do exactly the same operation as before. So I want to have just integral from variables t1, tn plus 1. Then I will denote this variable t as t1, and after we change such notation variables, we will get the formula n factorial, and here is again n plus 1 times integral from 0 to 1, and here is an t1 tn plus 1 square d t1 dtn plus 1. That's all. So this is another summa from the right part of our formula. You see the difference between these summas are only that we have here a permutation of the first two coordinates, yeah? And n minus 1. Now let us find the expectation of the left hand side. Yeah, I must erase everything here. Then we need to define what is E of x. As we remember, this is the Wiener integral of multiplicity n plus 1 from the kernel, new kernel, which is symmetrization an with respect to all variables en plus 1. Here is dw d1, dw dn plus 1. And before we study its expectation of the square, we have to write what is lambda an. What is lambda an explicitly? So let me do this. Lambda an of t1 tn plus 1. What is it? We must make symmetrization of the kernel an. And here it is already symmetric under permutations of all these variables beginning from the second to the n. So in order to have symmetric kernel, we just must put this variable, one variable tn, t1 on the every part of this formula, of this every place in this kernel. So I can say that it is equal to the following sum: 1 over n plus 1. Here we have a sum from k equal n plus 1. An, here we put tk, just one variable here. Excuse me, just a moment. Алло? Привет. Да, конечно, в 12. Все, договорились. A, N, E, K. And here we have T1. Just here is, excuse me, maybe T2 and so on. And here instead of K, I have T1. And then continue up to Tn plus 1. Yes. So the symmetrization is done if we just put every variable on the first place, because up to other permutations we have symmetricity. Now I will use this because here we have symmetricity with respect to all other variables, and then I can say that maybe it is enough to change two first variables. Yeah, because here it does not matter where T1 is placed. Yeah. Okay, I will use this. And now let's recall that expectation of the e of x square will be equal n plus 1 factorial. And here we have the multiple integral from 0 to 1 n plus 1 and lambda an square. I will not write all this. dt1 dt n plus 1. Then let us proceed as follows. We can try to write lambda an factorial using this representation. Then what we will have? First of all, we will have 1 over n plus 1 squared. So let us continue. It's equal to n plus 1 factorial divided by n plus 1 squared. Then multiply and sum. I will write multiple sum. And I will write this multiple sum as follows. One is when which is sum of squares, n plus 1. And here we have an t k t2 t1 in the case place tn plus 1 and here we have this is 1. The second sum will be sum from k is not equal to j. Let us remember that these two indices are from 1 to n plus 1. I will not write this in the blackboard, in the whiteboard. And here we have an. What we have here? tk, t2, t1 is a case place, tn plus 1. Multiply on an, and here we have tj, t2, t1 on the j place, and then tn plus 1, tn plus 1, and all this thing, all the sum will be integrated over dt1 dt n plus 1. Now let us work with separately with these two summas. That's what we will have. The first one does not depend from the notation of the variable, and it is understandable that the first summand can be transformed as follows. Here is, by the way, we cancel 1, so we have n factorial divided n plus 1, multiply again n plus 1 integrals 0, 1, n plus 1 multiplicity, an t1 tn plus 1 square dt1 dtn plus 1. Then let me again cancel this nominator, the denominator, and finally we get one of the summand which we already obtained. Yeah. This is the expectation of the square of the norm of our random function. So I can erase this one and continue to work with the last one expression. In the last expression, see what happened. Here, since symmetricity of an, we can do any permutation of this values. So here one can put here tj and all other values. And here one can put tk and all other values. So we have the same kernel, only first two coordinates are transmitted. So you can see that we get how many such summas. N plus 1. By the way, here we have already n factorial divided by n plus 1. But how many such summas we have? N plus 1 multiplied by n. Maybe yes. So we will have exactly the following. It is like the sum, and here yes. Let me check. And here we will have the integral of multiplicity n plus 1. Multiplicity n plus 1 0 1 and then an t1 t2 tn plus 1 and here we put the another kernel. Here we put another kernel, n. Here t2, t1, t3, and then tn plus 1, dt, tn plus 1. It seems that after we cancel the denominator here, we have to get the desired formula for our representation. It seems to be solved. Only let us check again this coefficient. Let us check again this coefficient for our derivative. Yeah. Let me recall you that when we discuss the derivative x t s, it was already n multiplied with kernel, this n minus time integral. Then when we calculate its expectation, and we did this, as you remember, we get n factorial multiplied by n. It's exactly because of this, it will be squared. Yeah. So everything is right, and we get second summa from our representation. Now our theorem is why? Because what is remaining to do? It is remaining to recall that extended stochastic integral is closed operator. So if the series of stochastic derivative will converge, then we will see that the series for integral will converge, and of course the resulting is the integral from the initial random function. So please complete the proof using the arguments that stochastic derivative and extended stochastic integral are closed operators. Now let us write again obtain the formula. So if there exists dx, then x belongs to domain of definition of extended stochastic integral, and expectation of e of x square is equal to expectation of the norm x square plus trace of dx square. Now let's see some examples where we will have some anticipated random function which will belong to domain of the extended or Skorokhod stochastic integral. This will show us that the name extended stochastic integral is really suited because E is extension of Ito stochastic integral. So let us see some examples. Let me consider the following example. Consider the random function of the following type. X of t is W1 minus W1 half multiply the indicator of 0 half of t plus of 0 minus W half multiplied on the indicator 1 half 1 of t. Let me firstly emphasize that this function definitely belongs to the domain of definition of the extended stochastic integral exactly due to the fact that it is stochastically differentiable. You remember that any polynomial from the value of inner process now is stochastically differentiable. So x, we know from our theorem that x belongs to the domain of E. And maybe it will be easy to get the representation of xt as a series of multiple integral. Now there's just one integral, so I can write that now xt is equal to integral from 0 to 1, a1 which depends on t, and t1 dw t1. And now what we have to do, we have to write explicit form of this a1 and do symmetrization in order to get extended stochastic integral. So let us write this. And A1 T1 is equal to the following. The indicator of 0.5 from T multiplied the indicator 1/2 1 from T1 minus indicator of 1/2 1 T multiplied with the indicator of 1/2 0 1/2 0 1/2. Please check this. And to do symmetrization, I will write a picture of this kernel. Write picture of this kernel. And if this is a square 0 1 0 1, here is 1/2 1/2 lines. Then if this is T and this is T1, then what we have? Firstly, when this is here, we have here 1, here we have 0, and here we have -1, and here we have 0. Yes, this is a step function of a square, which is equal 1 and -1 on the small squares and 0 on the diagonal squares. From this picture, it is trivial that lambda A1, T1, T2 is equal to 0. Correspondingly, extended stochastic integral from our function is equal to 0. So we have the following example. First, we have example of anticipating stochastic function belong to the domain of the extended stochastic integral. Second, we have the example of non-trivial random function for which extended stochastic integral of Skorokhod stochastic integral is equal to 0. Now let's go further and let us say that one of the powerful tools for studying extended stochastic integral is its definition like conjugated to stochastic derivative. From this point of view, it occurs that one can produce nice formula how we can put random constant under the sign of stochastic integral of outputted out stochastic integral. So here we again back to our students' years when we study usual integrals, and maybe when we started integrating by part formula, it was a desire of a lot of people just to output one function outside of integral. Of course, we cannot do this, but when we consider extended stochastic integral, we will invent the right rule how to do it. Okay, so what is the situation which we will discuss? Suppose that we have x, which is the function which has which belong to domain of definition of E, and alpha is stochastically differentiable, and I will suppose that alpha and d alpha are bounded. So they are operating as random function, but I will suppose that they are bounded. Random function. Then it occurs that the following formula, this is the theorem, the following formula holds. Alpha x, we multiply a random function, a random value, belongs to the domain of definition. And E of alpha x is equal to alpha e of x minus the integral from 0 to 1 x d alpha t dt. So you see, we have such a form of extracting random variable out of the sign of Skorokhod stochastic integral. Let's check this relationship. The proof is based on the integration by part formula, or on the what is the same on the definition of the extended stochastic integral. So we have that for any variable beta we belong to W1, we have alpha beta will also belong to W1. This is due to our restriction on the alpha. It is not only stochastically differentiable but bounded, and derivative is also bounded. So when we will do differentiation, everything will remain in the space of square integrated random functions. So one can check now that expectation of alpha x beta, excuse me, alpha x and integral from 0 to 1 x t d beta t is equal to I will write as follows: expectation integral 0 to 1 xt. Here is d of the product alpha beta of t dt minus I just recall it today already that stochastic derivatives satisfy all usual rules of derivative from the real analysis. So derivative of the product is alpha multiplies derivative beta plus beta multiplies derivative alpha minus the expectation, the integral from 0 to 1 xt beta d alpha t dt, and then let us use for the first 2 months the fact that x is in the domain extended stochastic integral. So I can continue and write the following. And write the following, that it is equal to e, here is beta, and here is alpha e of x. This is from this summand plus minus beta integral from 0 to 1 xt d alpha t t. Then let us put beta outside. Then what we will have? We will have that alpha x is in the domain of extended stochastic integral, because the equality holds for any beta, and that e of alpha x is exactly alpha e of x minus the integral from 0 to 1 x d alpha t x d t. That's all. We have the rule how to extract random variables from the side of extended stochastic integral. So now we have a good properties of extended stochastic integral, and next lecture we will use it to study existence of the density of solution to stochastic differential equation. For today, that's all. Thank you for your attention, and maybe somebody have questions or comments, please. Okay, if there are no questions, then thank you for your attention and see you next week. Bye.